Thanks, Ignacio and everyone. I'll try to be a little adaptive on my time schedule so that we can also have some meaningful panel discussion. Um, and I think a lot of great things have already been articulated about the challenges about, human and other non-human robotic missions to Mars. But stepping back from where I come from, I look at all space as great technological opportunities, and as reliable market estimates are putting it to be on a significant growth path, and many opportunities for access, communications, and in situ resource utilization, logistics, and so on, that can be, also great drivers for commercial products and driving the economy itself, and obviously AI and ML and advances coming in there can help provide a lot of the decision support systems for these technologies. Uh, Closer to Earth, but not really close, is our nearest celestial neighbor, our moon. And it's the space that includes Earth and Moon, and a little beyond Moon is what is loosely labeled as cislunar space. And that's where there's a lot of current interest. Obviously, the US has significantly returned to the moon, and China has done the same. And there's lots of other international actors that are doing the same, and obviously also commercial entities. And so, if you look at cislunar space, the White House had their first national cislunar strategy document that came out a couple of years ago. And as Ignacio mentioned, and also Luis previously, and Pascal talked about the NASA's the Moon to Mars architecture that's coming up. NASA is leading the development of coordinated lunar time. They have been tasked to do that. And obviously, there needs to be, if we talking about sustained operations at Mars, as a corresponding a Mars standard time to come up, especially in light of the lights, the speed of light delay that we're talking about. And closer home from where Luis and I are from in Texas, the Texas Space Commission was stood up a little over a year ago with the initial investment of $350 million, promoting and fostering development of commercial space operations, which not only includes cislunar space, but beyond. I mean, talking about the Moon to Mars architecture. So I think Luis embarrassed me by mentioning a few things about my research program and where I come from. Obviously, I'm from UT Austin. We bleed orange there. So this is not the correct shade of orange, but I'm sure you can understand it. And my own group has done a lot of work on guidance, navigation, control, including supporting intuitive machines. IM1 and IM2. We were bummed that IM2 could not stick their landing, and therefore we could not deploy Hopper, which was the propulsive vehicle that was designed to do extraterrestrial hops across the lunar surface. And we provided the control law for Hopper, so maybe there's a future mission to do that. And my group has also been extensively working in perception, especially computer vision. We were part of NASA's Seeker program, which is a 3U form factor CubeSat that was using monocular vision to do relative pose to a non-cooperative target on the range of several tens of meters standoff distance. So this Seeker monocular vision flew in 2019, just a few months before COVID hit. And that animation that you're seeing is live video from the experiment, the on-orbit experiment, which was successful. And we were able to deliver relative pose at 6 hertz on a single board computer on this 3U form factor CubeSat. So, uh, so uh, and obviously those are the building blocks for further advances that we are making in the perception space. Lewis is part of a joint project that we have funded from the U.S. Space Force, the SSTI, addressing in-space operations. So that's exciting stuff. Uh, the way I look at it is that, speaking especially of going to Mars, autonomy is not a choice, it's a necessity because of the fact that we don't necessarily have the access for ground support, especially for timely ground support. And so there's a lot of onboard decision making that you need to push in, especially for manned operations, but even for unmanned operations. And so there's got to be autonomy with those layers of safety and trust. And so I look at my three-legged stool of the research that needs to happen, and the algorithmic advances that need to come to fruition to enable these missions, that needs to have learning both off-board and on-board. Perception. I think Ignacio had a great chart where you need to make sense of what's happening, and then you need to go and figure out what strategies you would adopt to mitigate or to address, and then finally the implementation, the execution part. So that everything starts with that perception piece. And then the trust part, which captures the safety and especially human interactions are human rated missions where you clearly need to have some provability, some certifiability. So essentially, it's the dynamic nature of the missions that we need to field for, be able to adapt for unanticipated faults or tasks and users, and the scalability. So those are the research questions that my group has been addressing. Um, and specifically, we are looking at guidance or trajectory planning with those safety guarantees, so that you can, if you have a nominal path, but then something went wrong, can you revector yourself, and can you actually do that on board using either prior data, prior policies, or even some onboard learning. These are some projects that we have currently funded through AFOSR. We are looking at pre-positioning in the Sun, Earth, or the Sun, Mars uh, three-body system, certain resource hubs, or what you can call as depots, where you can even have safety or other equipment. You can quickly transfer astronauts or supplies, so that you can field these long duration space missions, especially human space flight missions. So those are some of the research thrusts that we are looking at. I think the challenges have been very nicely articulated, especially Pascal's presentation. When you go to Mars, I mean, beyond cislunar space, you're not just looking at patched conics anymore, in a sense that I think, I don't have the nice cartoon that Pascal had, but if you remember, there's a notion of how long it takes to go to Mars, and we have these rule of thumb estimates that take several years, or couple or 3 years, depending on how much time you want to spend at Mars. So these are what are designed based on patch conics. So you're looking at conic solutions, look in the heliocentric space to transfer you from Earth orbits to Mars orbits. But there needs to be optimization, and there also needs to be, especially when you want to exploit some of the multi-gravity or the multi-body dynamic regimes, you can have opportunities for faster transfers, or positioning these resource hubs that I mentioned about, so that they can be at Lagrange points in the Earth, in the Sun Mars three body system. You also have the vast asteroid belt, which is closer to Mars than here, and that could potentially provide access to some resources that you may be able to quickly leverage or bring over instead of transferring from Earth, right? So there could be a lot of optimization and trajectory design opportunities in this expanded multi-body environment. Um, Obviously, for crew safety and rescue considerations, the transit time is the biggest challenge that you need to address in one way or other. Uh, Mars has an atmosphere. Pascal had very nice descriptions and illustrations that we saw earlier about the nature of the atmosphere and also the thermal and environmental considerations that come about it. But the good news is that when you talk about Mars and exploring the Martian, planet, you are not necessarily restricted to surface robotic operations because there's an atmosphere. We had Ingenuity, and then I think Pascal talked about the next generation drone that you could potentially fly on the Martian surface. And so the fact that there is an atmosphere as thin or as um, low density as it is compared to Earth, you can still get some lift, and then you can actually fly over and then get some scientific measurements by expanding coverage, right? So you're not stuck to traveling on this rugged terrain, which requires again robotics of higher sophistication. So there's that trade-off. The other last thing that I want to mention about is PNT, positioning, navigation, timing. I already alluded to timing, especially if the need for a Martian standard, if you're talking about large scale or sustained operations in the Martian environment. But part of that is navigation. DSN is overly subscribed and taxed, and so even if you are talking about having Earth support or ground support, at some point, depending on how many missions you have and at the scale at which you are operating, you certainly need to be looking at setting up some sort of a scalable architecture for navigation in the Martian environment, Martian region. And is that something that replicates GPS, GNSS, or and this is also where there's a significant deviation from what we are looking at for cislunar. Closer to the moon, you can still operate based on optical navigation or crater-based navigation if you're really close to moon, and you can have assets on the moon. And you're in Mars orbits or low Mars orbits, because of the fact that there's atmosphere there, you can't really do a lot of crater-based navigation. So you're also constrained in other ways in terms of the fact that you need to be able to handle those Mars reentry and other conditions that produce these significant blackouts during a large part of the entry, descent, landing segments, and also the thermal loads that you experience because of the entry conditions. And so, but the key challenge really is to be able to provide those PNT solutions, or to think of what architectures that we can have so that you can navigate yourself in the Martian environment. So I'm going to stop here, and I'm sure we'll have some time, or we want to save some time for some discussion here. But I would thank you all again for this opportunity.
Okay, we're going